Hello everyone. Today we will discuss about dielectrics. A dielectric is a substance which does not allow the charge to pass through it but allows the charge to exert electrostatic force on one another. It is essentially an insulator which can be polarized through a small localized displacement of its charges. Most of the capacitors have non-conducting materials or dielectrics between the plates. If I will talk about a common type of capacitor, then it consists of two long metal strips as a conducting plate and a insulating material like plastic or mylar between them as a dielectric. A sandwich of these materials are rolled up to form a unit that gives a capacitance up to few microfarads. Placing a dielectric between the plates of a capacitor serves three functions. First, it solves the mechanical problem of maintaining two large plates at a very small separation without its actual contact, as I told you that the sandwich is rolled up. Second, the dielectrics increases the maximum possible potential difference between the plates. And the third one, the capacitance of a capacitor of given dimensions is greater when there is a dielectrics between its plates than when there is a vacuum. So, inserting the dielectrics between the plates of a capacitor makes these three useful functions. Let us assume that the original capacitance of a capacitor is C0. So, I can write C0 as Q by V. And the capacitance when a dielectric material is placed between the plates is C, so it can be written as Q by V, since we know that on introducing a dielectric material, the potential difference between the plates will change. Now, as from the previous discussion, you know that if you will insert a dielectric material, the potential difference between the plates must decrease. So this V must be less than the previous case where there was air between the plates of capacitor, and from this you can easily conclude that this capacitance with the dielectrics must be greater than the capacitance of the capacitor when there is a air between the plates. It means that on introducing the dielectrics, the capacitance of a capacitor increases. Now, if I will find the ratio of these two, so the capacitance of a capacitor with dielectrics and the capacitance of a capacitor without dielectrics, this ratio is termed as K, where K is the dielectric constant of that dielectrics. In other words, as we know that we can write charge as C0 V0, and with dielectrics the charge can be written as CV. Since the charge on both the plates is same, because my capacitor is not connected with the battery, so the charge will remain constant. If I will apply this condition over here, we will get that K equals to V0 by V. Here you can also define the dielectric constant in terms of the potential difference between the plates of capacitor in presence of dielectric and in absence of dielectrics. So, as we know that the dielectric constant is V0 by V, or you can write that the potential difference between the plates decreases by a factor K. Now, if the potential difference of a parallel plate capacitor, I am just taking right here, say it is a parallel plate capacitor, and this is the electric field. This is plus sigma and this is minus sigma. These are the charge densities. So the potential difference decreases by a factor k. It means that the field must decrease by the same factor as potential. Now, since the electric field is decreased by the factor k, then what is the reason or how this electric field decreases? So the idea is that the charges, these charges on the plates are producing this electric field. If the electric field is decreasing, then you may have a thought that the charges or the charge densities of the surface changes. But the answer is that charge is kept constant. So if the charge is constant on the plates of a capacitor, it means the charge density will not change at all. So what is happening? Who is decreasing the electric field by this factor? So the answer for the same is the dielectric. What happens? You can see that if I will place a dielectric between the plates of this parallel plate capacitor, then the induced charges, or you can say the charge density with opposite polarity, it means if it is a plate with positive charge density, so the induced charge density with negative sign will be here, and for this plate I can write the induced charge density, or you can say the charges appears or induced with the opposite polarity near the plates, and these induced charges arises as a result of redistribution of charge inside the dielectric, since my dielectric is present in this field. It means the electric field is redistributing the charges inside the dielectrics, and that's why there are some charges that are appearing on the opposite faces of this dielectric, and this dielectrics is producing a kind of induced electric field inside it from right towards left. My actual electric field was from left to right, and this induced electric field is decreasing the net electric field between the plates of my capacitor. So I can say that net electric field when dielectric is kept between the plates is electric field when there was no dielectric, that is E naught, minus the induced electric field produced inside the dielectrics. So this is the reason how electric field between the plates of a parallel plate capacitor decreases. And this phenomena of redistribution of charges inside the dielectric is called polarization. Now, if I will find out the field when there was no dielectric, and this case when the dielectric is present between the plates of capacitor, I can write that when there is no dielectrics, the electric field between the plates is sigma by epsilon naught. For this case, we can just assume that the resultant charge density on the plates is sigma minus sigma I. So for this case, when the dielectric is completely filled between the plates, I can write field as sigma minus induced charge density and divided by epsilon naught. So these are the fields with dielectric and without dielectrics. And if you will simplify, you will get sigma induced charge density as charge density in bracket 1 by, or simply if you will replace the charge density by charge per unit area, so we will get induced charge as charge on the plates by this. So with this you can find out the induced charge and the induced charge density Now we will discuss the mechanism of the charges induced on the surface of dielectrics when it is placed between the plates of capacitor. So, if I am having a conductor that is placed in an external electric field, so you can say that suppose it is a conductor and it is placed in this external field E naught. So since my conductor have number of free electrons, so the charges, positive charges will experience a force in the direction of field, while the negative charge will experience a force in opposite to that, and these free charges will appear here like this, and a field will produce inside this conductor in opposite to the external field, and let me call this field as EI, such that this induced field is exactly same as the external field. So the net field inside a conductor is always 0, and you can see that these charges are free charges, since it is a conductor. Now what will happen if I will place a dielectric material in presence of external field? Now since it is a dielectric, so the charges are not free as it was in case of conductor. In fact, the charges are bounded to a molecule, and these kind of charges are called bound charges. But due to the presence of external electric field, the charge density will be here on the opposite faces of this dielectric, and induced electric field will produce inside the dielectric, but this induced field inside the dielectric is very less in comparison to the external field. And now we are going to discuss how these charges are appearing on the walls of a dielectrics when a dielectric is subjected to an external electric field. Now, a dielectrics can be classified in two types. One, a dielectrics that contains polar molecules, and the dielectrics that contains non-polar molecules. So let us understand what are polar and non-polar molecules. So first we will discuss polar molecules. In a polar molecule dielectrics, the center of mass of the positive charge and the center of mass of the negative charge do not coincide. It means both the centers have a separation between them, and that produces a dipole moment within the molecule. You can see the example of such polar molecules like HCl. So you know that in HCl, since chlorine is much more electronegative, so it will attract the pair of sharing electron and it will get a partial negative charge, and here hydrogen will get a partial positive charge. So due to these induced charges, a dipole is formed. As you can see that both are equal and opposite charges, and the net dipole moment P will be directed from this side to this side. So just like HCl, we have another case like water. So in water also you have two separate dipoles. One is framed by this oxygen and hydrogen, and the other one by this oxygen and this hydrogen. I can write it like this too. And as you can see, this is the dipole moment of this dipole, and this is the dipole moment of this dipole, which will result the net dipole moment in this direction. So a polar molecule dielectrics have permanent dipole moment with them. Now, since all these polar molecules are randomly distributed within the dielectrics like this, So since they are randomly distributed, so the net dipole moment of the substance is 0. Or you can say that they will produce no electric field within the substance since these polar molecules are randomly distributed. Now, when I will subject these molecules in an external field, say E naught, then these dipole moment tries to align themselves in the direction of electric field, as we have seen the example that when a dipole is placed in electric field, it experiences a torque. So in presence of electric field, they will align themselves in the direction of electric field like this, and in that case the net electric field inside it is not 0, and it results the induced charges on the boundary of the dielectrics. Now we will discuss the dielectrics with non-polar molecules. So a molecule in which center of mass of positive charge and the negative charge coincides with each other are called non-polar molecules, and the dielectrics with the same molecules is called dielectrics with non-polar molecules. For an example, the molecule of chlorine, oxygen and nitrogen. So in case of non-polar molecules, the center of mass of positive and the negative charges coincides with each other, and that results net 0 electric field inside the substance. Now what will happen if I will subject such kind of dielectrics with non-polar molecules in electric field? So if they are placed in external field, in that case the field exerts a force on the positive charge towards its direction and the negative charge on the opposite side of its direction, and the final situation becomes like this. Remember that whether a dielectric is having polar molecules or non-polar molecules, the net charge inside the dielectrics is always 0, whether you will subject it in an external field or not. As you can see, in this case, when there is no external electric field, the net charge is 0, and here also the net charge on the dielectrics is 0, but there is a shifting of the charges due to the presence of electric field, and this shifting appears as a result of charges on the opposite walls of dielectrics. As you can see that these charges are appearing on the face and these negative charges are appearing on this face, and if you will simplify it, you can generally write that a positive charge will appear here and the negative charge will appear here, and that will produce an induced field inside the dielectrics, and this direction is opposite to the direction of applied external field, so it decreases the net field inside the dielectrics. So both polar and non-polar dielectrics develop a net dipole moment in presence of external field, and this fact is called polarization of dielectrics. Now consider a case that this is a parallel plate capacitor with charge densities, and when a dielectric is placed, let the induced surface charge densities are, the separation between the capacitor is D and the area of this is A. So the dipole moment induced per unit volume is defined as polarization density. So if I can write the definition in mathematical form. So polarization density is net dipole moment per unit volume. So net dipole moment is basically the charge, let the charges are Qi on the opposite walls of this dielectrics. So the dipole moment will be the charge multiplied by the separation and divided by the volume, that is nothing but the area into distance. Now, if I just needed to find out the induced charge density, I can write charge density as induced charge by area. So my induced charge is charge density multiplied by area, and if I will place it here, I will get P as sigma R. So polarization density may be defined as the induced charge density on the surface of dielectrics. Now just keep in your mind that how this charge densities are produced. Basically they are produced in the presence of external field. So consider that initial external field was E naught and the induced electric field inside the dielectric is EI. So I can write the net electric field as E naught minus EI. Now this is the effective electric field between the plates of capacitor, and this net electric field between the plates of capacitor will decide the polarization density. It means if this net electric field inside the plates is strong, then the polarization density will also be strong. And if you can see, the direction of the dipole moment is from negative to positive. So the dipole moment is in the direction of field applied, or you can say net electric field, that will also be in this direction because E naught is greater than EI. So I can write that this polarization density is directly proportional to the net electric field between the plates of a capacitor. And if I will remove the proportionality sign, I will get this constant, and this psi constant is called electric susceptibility. And this electric susceptibility describes the electrical behavior of dielectrics. Now we will consider a case when a dielectrics is placed between the plates of capacitor, but it is not completely filled. So suppose D is the separation between the plates of capacitor, and let me take the charges as plus Q and minus Q. So the original electric field due to the charges on the plates is E naught, and we know that if it is a dielectrics of same area and thickness T placed between the plates, then the induced charges will appear on it like this. So there will result a induced field inside the dielectrics, and that will decrease the value of the net field inside the dielectrics as E naught minus EI, that is the induced field. And we also know that I can write the net field inside the dielectrics, that is E net, or simply E, as E naught by K, where K is the dielectric constant of this dielectrics. It is from the previous study. So now inside the dielectric the net field is this, and in a region when there is a air, the field will be E naught. So I can easily calculate the net potential difference, and that is the field in air multiplied by the separation. As you can see that T minus T is the place where there is air, plus the field that is inside the dielectrics multiplied by the separation, and this net electric field E is only in this separation T, so I will multiply it by T, and on simplifying we can write it as E naught D minus T plus, this is the field, net field, so I can write it like E naught by K T, which on simplifying gives, or you can write the value of the field that is between the plates, and that is sigma by epsilon naught times this quantity. So once the potential difference is known, we can find out the capacitance by the definition that it is the charge divided by the potential difference. So this is charge and the potential difference. I can write this charge density as charge by area, and this is going to be, which on simplifying will give you this A epsilon naught divided by D minus T plus T by K. So this is the capacitance of a parallel plate capacitor that is partially filled with the dielectrics up to distance T. Now, a very important outcome can be taken from this concept, that suppose in place of this dielectrics I am having a conducting plate of same area and same thickness. So this is my conducting plate, and if it is a conducting plate, you know that the net field inside it must be equal to 0, and also that K is infinite for a conducting plate. So I will place a conducting plate of same area of thickness, then in that case the capacitance, this will turn out to be A epsilon naught divided by D minus T only, because this term is going to be 0 for conducting plate. So with that we can find out the capacitance when a conducting plate is placed between the plates of a capacitor.